All right, let's dive into a really fascinating little spatial puzzle today. This one comes from a problem set at MIT, and it's called the case of the disagreeable vectors. It seems so simple on the surface, but trust me, it reveals something really profound about how we describe directions in space. So here's the question that kicks everything off, and it almost sounds like a riddle, right? Imagine you've got a flat surface, like a piece of paper. Can you draw 3 arrows, all starting from the very same point, so that every single one of them is pointing, generally away from the other two, so that each pair kind of disagrees with each other? Okay, so in the language of linear algebra, that question looks like this. It's asking if we can find 3 vectors, let's call them u, v, and w, where the dot product between every pair is a negative number. Now, that might look a little abstract, but that little less than 0 symbol, that is the absolute key to this entire mystery. So to solve this thing, we've got to figure out what that clue really means. Which brings us to our first section. We need to unlock the meaning of the dot product. This isn't just some random calculation your math teacher made you do. It's an incredibly powerful tool that tells us something fundamental about the geometry between vectors. So what is it? Well, think of the dot product as a secret decoder. You take 2 vectors, you do this special kind of multiplication, and out pops a single number. And that number isn't random. It tells you a secret about the relationship between the 2 directions you started with. And here's how it works. This formula is the whole shebang. It says the cosine of the angle between 2 vectors is directly connected to their dot product, that v dot w on top. Now the stuff on the bottom, the v and w, those are just the lengths of the vectors. And here's the thing about lengths. They're always positive. So the sign of the whole equation, whether it's positive or negative, comes entirely from the dot product. And that leads us to the crucial clue. If the dot product is positive, it means the cosine of the angle is positive, which only happens when the angle is sharp or acute, less than 90 degrees. But if the dot product is negative, the cosine is negative, and that means the angle has to be wide or obtuse, greater than 90 degrees. And that's it. That's what pointing away means in math, a negative dot product. So now that we have our clue, we can go back and crack this case. All right, we are armed with our new secret weapon, the knowledge that a negative dot product means an obtuse angle. So let's see if we can actually find 3 vectors where every single pair disagrees. Remember, that just means the dot product for every pair has to be negative. Now, the source material actually gives us a set of suspects. We've got vector u, which just points straight to the right along the x-axis. Then we have v and w, which both point a little backward and then split off, one going up and one going down. Just looking at these coordinates, though, it doesn't really give you the full picture, does it? So, what happens when we actually plot these things? Well, would you look at that? They arrange themselves perfectly, pointing out from the center like the spokes of a wheel, with about 120 degrees between each one. You can just see it. That looks like it works. The angle between any 2 of them is definitely wider than a right angle. Our intuition is screaming yes. But, intuition isn't proof. We have to do the math, we have to check the dot products. So you take any pair you want, u and v, v and w, u and w, you run the calculation and you get the exact same result every single time, -1/2. And there you have it. The math confirms what our eyes were telling us. Since every dot product is -1/2, it means every single angle between these vector pairs is greater than 90 degrees. They are all, officially, disagreeing with each other. The answer to that puzzle from the beginning? It is a definite, proven yes. Okay, so cool. We solved a neat little brain teaser, but so what? What's the big takeaway here? Because this actually points to a much bigger, much more important idea. This is why this stuff is so amazing. Our intuition, our brains might struggle a little to imagine 3 things that are all pushing away from each other. It feels kind of crowded, right? But a tool like the dot product doesn't have to guess. It proves. It gives us a precise language to describe space with a certainty that goes way beyond what we can just sketch with our eyes. We took a vague idea pointing away and turned it into a provable fact. That's the real power here. And that's what I want to leave you with. If a simple question about 3 little vectors can lead us to this kind of insight, just imagine what other surprising, beautiful geometric truths are hiding out there in plain sight, just waiting for us to find the right mathematical language to uncover them. Thanks for joining me.